Right now, as you watch this, something is happening that nobody can stop. Not governments, not scientists, not the laws of physics themselves. The universe, every galaxy, every star, every atom of matter that has ever existed, is slowly, silently, inevitably dying. And the terrifying part? It already started. Billions of years ago. Without asking permission, today we're going to do something that no human being has ever physically done. We are going to travel to the absolute end of time, past the last star, past the last atom, past the last moment when anything at all, can still happen. And then we are going to look at what comes next. Because there is something that comes next. And it is the strangest, most unsettling, most philosophically devastating thing that physics has ever discovered. Let's start with something simple. Look up at the night sky. On a clear night, far from city lights, you can see roughly 5,000 stars with your naked eye. 5,000 points of light scattered across the darkness. It feels enormous. It feels infinite. But here's what you're actually looking at. Every single one of those stars, every single light you can see, belongs to just one galaxy. Our galaxy, the Milky Way. And the Milky Way contains somewhere between 200 billion and 400 billion stars. Let that number exist in your mind for a moment. 400 billion stars. Just in our galaxy. And there are 2 trillion galaxies in the observable universe. 2 trillion. If you counted one galaxy per second, without sleeping, without stopping, without a single break, it would take you 63,000 years just to finish counting. This is the universe. It is vast beyond any human intuition. It is ancient beyond any human calendar. It is so large that the light from the most distant galaxies we can detect has been traveling toward us for over 13 billion years, and it still hasn't reached us yet. And yet, all of this, every galaxy, every star, every nebula, every planet, every particle of hydrogen drifting silently through the void, all of it is dying, not metaphorically, not philosophically, physically, measurably, irreversibly. The universe has a death clock, and it is already counting down. To understand how the universe dies, you first need to understand a law so fundamental, so absolute, so unforgiving, that physicists call it the most powerful law in all of science. The second law of thermodynamics. Here's what it says. In plain language, everything always moves from order to disorder. Always. No exceptions, no loopholes, no escape. Think about a cup of hot coffee sitting on your desk. Left alone, it doesn't stay hot. It cools down. The heat spreads out into the room. The energy disperses. And no matter how long you wait, that heat will never spontaneously gather itself back into the cup and make your coffee hot again. That is entropy. The relentless, one-way flow from concentrated order to scattered chaos. Drop an egg on the floor. It shatters. You will never ever watch the pieces spontaneously leap back together and reform a perfect egg. Never, not once in the history of the universe, burn a piece of paper. The ashes, the smoke, the released carbon dioxide. They will never reassemble themselves back into paper. Not in a million years. Not in a billion. Entropy only increases. Always. In every system. In every corner of the universe. And here's the terrifying implication. If entropy always increases, if everything always moves from order to disorder, then the universe itself has a direction. A trajectory. An arrow. And that arrow only points one way. Toward maximum disorder. Toward a state so completely, so utterly disordered, that nothing can ever change again. Physicists have a name for this final state. They call it the heat death of the universe. And it is the most inevitable event in all of existence. Now I want to take you somewhere most people never go. I want to take you through the actual timeline of how the universe dies. Because this is not a vague, distant, abstract philosophical concept. This is a sequence. A series of specific events. Each one more extreme than the last. Each one closing another door on the possibility of anything happening ever again. Fasten your understanding. Because the scales of time we're about to discuss will make the age of the universe, 13.8 billion years, feel like the blink of an eye. We live in what cosmologists call the stelliferous era, the age of stars. This is the golden age of the universe, the period during which stars are being born, burning brilliantly and lighting up galaxies across the cosmos. Right now, the universe is alive with stellar fire. But even now, in this golden age, the death has already begun. The most massive stars, the giants, the supergiants, the brilliant blue monsters that burn 1,000,000 times brighter than our sun, they are already dying. They burn so hot, so furiously, that they exhaust their fuel in just a few million years. They explode in supernovae. They collapse into neutron stars and black holes. They go dark. Our sun is middle-aged. It has been burning for 4.5 billion years. It has roughly another 5 billion years of fuel remaining. But the small stars, the red dwarfs, they are the survivors. Dim, cool, miserly with their fuel. A red dwarf star burns so slowly, so efficiently, that it can last for 10 trillion years. That's 10,000 billion years, slowly, Over the next 100 trillion years, the last red dwarfs will exhaust their fuel. One by one, across trillions of years, the lights will go out. And when the last red dwarf finally dies, the universe will never make a new star again, because the raw material, the hydrogen gas clouds that gravity collapses into new stars, will be gone, used up, spread too thin, too cold, too diffuse to ever collapse into nuclear fire again. After 100 trillion years, the age of stars will be over. Forever, after the last star dies, the universe enters what cosmologists call the degenerate era. The galaxies will still exist, but they will be dark, ghost galaxies, filled not with burning stars, but with the cold, dense remnants of dead stars, white dwarfs, neutron stars, black holes. The universe will be an enormous, cold, almost completely dark sea of stellar corpses. Occasional collisions will happen. Two white dwarfs might drift toward each other over billions of years, slowly spiraling inward and finally collide, releasing one brief flash of energy in the overwhelming darkness. A tiny momentary spark in an ocean of cold black. But even these pale echoes of stellar fire will eventually stop. And then something stranger happens. Protons, the fundamental particles at the heart of every atom that has ever existed, may decay. This is one of the most profound and unsettling predictions in modern physics. Current theories suggest that protons are not eternal. They are stable for an almost incomprehensibly long time. Current estimates suggest a proton lives for at least 10 to the power of 34 years. That is a 1 followed by 34 zeros. But eventually they decay. And if protons decay, then matter itself is not permanent. Every white dwarf, every neutron star, every dead cold dark lump of matter drifting through the black void, slowly, across timescales that make the current age of the universe look like a nanosecond, they will dissolve, atom by atom, particle by particle. The matter of the universe will evaporate. By the end of the degenerate era, the last white dwarf will have faded to black. The last neutron star will have cooled to nearly absolute zero. And matter, solid, touchable, real matter, will be vanishingly rare in the universe. What remains? Black holes. The black hole era. 10 to the power of 40 to 10 to the power of 100 years in the black hole era. The universe belongs entirely to black holes. Everything else is gone. Every star, every planet, every asteroid, every drifting cloud of hydrogen, every dead white dwarf, every cold, dark neutron star. Gone. The universe is now almost perfectly empty, almost perfectly cold, almost perfectly dark, almost, because scattered across the unimaginable vastness of this dead, dark cosmos, black holes still exist. The same black holes that formed from dying stars, the supermassive black holes, at the centers of galaxies. These gravitational monsters have been slowly, patiently, silently accumulating everything around them for hundreds of trillions of years. And now they are the last structures of any significance in the universe. But here, something extraordinary happens. Something that one of the greatest physicists of the 20th century discovered. Something so counterintuitive, so strange, so beautiful in its mathematical elegance, that it changed our understanding of everything. Stephen Hawking proved that black holes are not truly black. They radiate. Through a quantum mechanical process now called Hawking radiation, black holes slowly, unimaginably slowly, leak energy. Particle by particle, quantum by quantum, they evaporate. The rate of evaporation is almost beyond comprehension. A stellar mass black hole, one that formed from a star roughly the mass of our sun, would take 10 to the power of 67 years to completely evaporate. The supermassive black holes at the centers of galaxies, those take 10 to the power of 100 years. But they do evaporate, inevitably, completely, without exception, one by one across timescales so vast they have no name in any human language. The black holes will flicker, fade, and disappear. And when the last black hole evaporates, something happens. Something that changes everything. This is the moment we came here for. The last black hole in the universe has just evaporated. In its final moments, it released its remaining mass as a burst of Hawking radiation. A brief flash of photons and other particles scattered into the void. A dying scream of quantum energy. And then silence. What does the universe look like now? There are no stars. There have been no stars for so long that the concept of a star has no physical meaning. There are no planets, no asteroids, no gas clouds, no dust. There is no matter. The last proton decayed so long ago that matter, solid touchable matter, is just a theoretical memory. There are no black holes. The last one just died. What remains? Photons, neutrinos, electrons, positrons, lone particles, spread so impossibly thin across such an incomprehensibly vast space that the average distance between any two particles is larger than the observable universe is today. The temperature of the universe at this point approaches, but never quite reaches, absolute zero, the theoretical minimum temperature, the point at which there is no thermal energy whatsoever. The universe is, for all practical purposes, empty, And here is the most devastating, most profound, most philosophically staggering part. Nothing can happen. Think about what that means. Truly think about it. Every event that has ever occurred in the history of the universe, every star that ever burned, every planet that ever formed, every ocean that ever moved, every thought that was ever thought, every life that was ever lived, all of it required energy flowing from a concentrated source to a dispersed sink. Fire needs fuel and oxygen and a temperature difference. Life needs food and sunlight and chemistry. Thought needs glucose and oxygen and electrochemical gradients. All of it. Every single thing that has ever happened required a difference, a gradient, a place where energy was concentrated and another place where it wasn't. In the final state of the universe, in the heat death, there are no differences. Everywhere is equally cold. Everywhere is equally empty. Everywhere is equally dark. There is no temperature gradient anywhere in the universe. None. Not even a tiny one. And without a temperature gradient, no work can be done. No process can occur. No event can happen. The universe is not just dead. It is in a state where death itself has died. And now we arrive at the question, the real question. The one that keeps cosmologists awake. The one that sits at the absolute boundary of what physics can say. What happens 1 second after this? 1 second after the last black hole evaporates. 1 second after the last photon scatters into the void. 1 second after the universe reaches maximum entropy, what happens next? And here physics does something extraordinary. It hesitates because there are 3 possibilities, 3 doors. And behind each door is a different kind of answer, each one more unsettling than the last, or one. Eternal staticist first possibility is the one most physicists lean toward. Nothing happens. Nothing ever happens again. The universe sits in its final state. Cold, empty, dark, perfectly uniform. For an eternity. Not just billions of years. Not just trillions. For a time so long it has no end, no boundary, no conceivable conclusion, forever. And here is what makes this so philosophically devastating. In this scenario, the universe doesn't end. It continues to exist, technically. Every second continues to tick forward. Time continues to pass, but nothing changes. Every second is identical to every other second, perfectly, absolutely, completely identical. Is that existence? Is a universe that exists but cannot change still a universe in any meaningful sense? Is time still real if nothing ever happens to mark it? These are not just philosophical questions. They are questions that the physics of thermodynamics forces upon us whether we want to face them or not. The stunt possibility sounds like science fiction, but it is mathematically real. In the 19th century, French mathematician Henri Poincaré proved a remarkable theorem. He proved that any closed system, any finite collection of particles bouncing around in a finite space, will, given enough time, return to a state arbitrarily close to any previous state. Given enough time, the particles will rearrange themselves randomly, by pure chance, by the statistical fluctuation of quantum uncertainty. And if you wait long enough that the timescale makes the heat death of the universe look like a brief moment, you would expect by pure probability for particles to randomly assemble themselves into things. A hydrogen atom, a star, a planet, a molecule of water, a strand of DNA, a brain. Not because of any intention, not because of any design, but because in infinite time all possible configurations of matter will eventually occur. Simply because they are possible. The Poincaré recurrence time for a system the size of our observable universe is approximately 10 to the power of 122 years. This number is so large, it cannot be meaningfully visualized. It dwarfs the heat-death timeline the way our universe dwarfs a single atom. But it is finite, and in principle, in the cold, dead, empty universe of maximum entropy, there is nothing to prevent quantum fluctuations from randomly assembling over this incomprehensible timescale, a complete working brain, a brain with memories, a brain with experiences, a brain that believes it has lived a full life, when in fact it has just spontaneously materialized out of random particle fluctuations in an otherwise dead universe. Physicists have a name for this disturbing theoretical entity, a Boltzmann brain. A consciousness that blinks into existence for a moment, with complete detailed false memories of a life that never happened, and then dissolves back into chaos. And here is the thought that makes this truly unsettling. If Boltzmann brains are possible, if they will inevitably occur given enough time, then there is no way for you to know, right now, that you are not one. There is no experiment you can perform, no observation you can make, no thought you can think that would definitively prove that your memories are real, that the universe around you is real, that you are not simply a random quantum fluctuation that materialized in the dead, cold, empty cosmos. Already convinced that you had a childhood, a life, a world. This is not a metaphor. This is a genuine, unresolved problem in modern physics and philosophy of mind. The third possibility is the most immediate, the most visceral, the most terrifying, and it may already be happening. Right now. In this moment. As you watch this, in quantum field theory, the vacuum of space, the empty space between particles, has energy. The vacuum is not nothing. It is a quantum field in a particular energy state. And here is the thing about energy states. They can be stable, like a ball sitting at the bottom of a valley, or they can be metastable, like a ball sitting in a small dip on the side of a hill, stable for now, but one small push away from rolling all the way down. The question, and it is one of the most actively researched questions in modern physics, is whether the vacuum of our universe is in its true lowest energy state, or whether it is in a false vacuum, a metastable state, a small dip on the side of a hill. If our vacuum is a false vacuum, then somewhere, at some random point in space, at some random moment in time, quantum tunneling could cause a bubble of true vacuum to spontaneously form. A tiny bubble, perhaps the size of a single proton. Inside this bubble, the laws of physics are different. The energy of the vacuum is lower. The constants of nature are different. The rules that govern matter and energy and chemistry and biology, all different. And this bubble expands. It expands at the speed of light, in every direction, simultaneously, unstoppably. You cannot see it coming. Nothing can see it coming, because nothing in the universe travels faster than light, and the bubble wall travels at the speed of light. There is no warning, no signal, no indication. One moment, everything is normal. The next moment, the bubble wall has passed through your location. And in that passing, every atom in your body is restructured according to a completely different set of physical laws. In an instant too small to measure, every chemical bond, every atomic structure, every particle interaction that makes up what you are, simply ceases to exist in its current form, not an explosion, not a destruction in any conventional sense, more like a cosmic reset, a rewriting of the physical laws in your location. Spreading outward at the speed of light, the old universe dissolving behind the advancing wall, like a sandcastle dissolving in an advancing tide. And the most disturbing part? The Higgs field measurements from the Large Hadron Collider suggest that the vacuum energy of our universe may indeed be metastable. The universe may right now be in a false vacuum. The bubble may have already formed somewhere. In some distant galaxy, billions of light years away, expanding toward us right now, at the speed of light, we wouldn't know. We couldn't know. Until the moment it arrived, which would also be the last moment of anything. Now step back, take a breath, and feel what you're feeling right now. Because this is the part that Feynman always insisted was the most important part of any scientific understanding. Not the equations, not the timelines, not the technical vocabulary, the feeling of understanding something true about the universe, really true, not comforting, not designed for your benefit. Just true, the universe will end everything. Every star, every world, every living thing, every thought, every love, every achievement, every moment of beauty or terror or wonder will eventually reach a state from which no further change is possible. That is a fact, not a belief, not a theory in the colloquial sense, a scientific description of where physics inevitably leads. And in the face of that fact, three things tend to happen to people. Some feel despair, the smallness, the brevity, the apparent meaninglessness of anything that lasts for only a finite time in a universe that has essentially infinite time ahead of it. Some feel relief. Strange as that sounds, there is a kind of peace in understanding the deep structure of reality, in seeing clearly, without illusion, what the universe actually is. And some, and this is the group Feynman always belonged to, feel wonder, pure, electric, overwhelming wonder. Because here is what also true, the universe is dying. And in the middle of its dying, in this astonishing, brief, golden period, it produced complexity, it produced chemistry, it produced biology, it produced nervous systems, it produced brains that could look up at the sky and ask questions. It produced you. You are not separate from the universe. You are not an observer watching from outside. You are the universe, locally, temporarily, observing itself. You are 13.8 billion years of physics that has somehow folded back on itself and become aware. And you are doing something that, as far as we know, no other arrangement of matter in the observable universe has ever done. You are understanding. You are sitting here, made of carbon and hydrogen and oxygen and iron, forged in the cores of ancient stars. And you are comprehending the end of everything. The universe will reach maximum entropy. It will reach the state where nothing can ever happen again. But right now, in this moment, something is happening. You are thinking. And that, in the grand, cold, indifferent mathematics of entropy, is extraordinary. There is a question that the philosopher Gottfried Leibniz asked 300 years ago. A question so fundamental that no one, not a single philosopher, physicist, mathematician, or theologian in 3 centuries, has given an answer that fully satisfies. Why is there something rather than nothing? The universe didn't have to exist. Physics tells us that. The laws of physics themselves didn't have to exist. There is no known reason why there should be a universe rather than a perfect, eternal void. And yet here it is. Here you are. 13.8 billion years of cosmic evolution, played out across 2 trillion galaxies, produced, among countless other things, a conscious entity sitting here right now, watching this, thinking about the end of everything. When the last black hole finally evaporates, in 10 to the power of 100 years from now, there will be no one there to watch, no one to mark the moment, no thermometer to record the final cooling, no consciousness to register the last flicker of Hawking radiation, just silence, just uniformity, just the cold final equilibrium of maximum entropy. But right now, in this ridiculous, beautiful, cosmically unlikely sliver of time, there is light, there are stars, there is a planet where liquid water moves across ancient rock. There are minds that ask questions. And somewhere in that asking, in that fundamental human refusal to look away from the hardest truths, there is something that feels against all the cold mathematics of entropy, like meaning. Physics doesn't tell us what to do with that feeling. That part, it seems, is still up to us.